So welcome back. We have been discussing on the properties of monosaccharides and we just completed the stereoisomerism as well as reducing ability. And the next one is the epimers of monosaccharides. Epimers, what are epimers? Two sugars or monosaccharides that differ only in the configuration of substituents around one carbon atom. It is known as epimers. Okay. So here we have a typical example of D-glucose and D-mannose and D-glucose and D-galactose. First one we will see this way. Okay, so these two are considered as epimers at carbon 2. Okay, so that has to be specified when we are speaking about epimers. At which carbon the pair it is like different. Okay, so here you can see when we take glucose, we have all these D-glucose. Okay, glucose because at C3. Except for C3, in all other cases, hydroxyl group is on the right side. Okay, D form because the fifth carbon atom has a hydroxyl group on the right side, isn't it? So it is D-glucose. Now, in the D-glucose and D-mannose, they differ only with respect to the configuration or arrangement of the constituents around the second carbon. Okay, so these two are epimer at carbon 2. While D-glucose and D-galactose, these two are epimers at carbon 4 because all other carbon atoms do have their substituents arranged in the similar way in both the molecules when we compare. But at C4, it is different. Okay, hydroxyl group is on the right side in glucose while it is on the left side in D-galactose. So these two are one set of epimer and D-mannose and D-glucose is another set of epimer. Okay, I hope it is clear. Now, anomerism. So before we go into anomerism, we need to know that the monosaccharides, we can exist in linear chains like this and also in cyclic form. Okay, so before we go into anomerism, we need to know the cyclization of monosaccharides. Okay, we can see cyclization here. The aldehyde and ketone moieties or the group of the carbohydrates with 5 or 6 carbon will spontaneously react with alcohol groups present in neighboring carbons to produce intramolecular hemiacetals or hemiketals respectively. It's simply put in another way, the 5 carbon, 6 carbon containing monosaccharides, that is pentoses and hexoses, what happens is the aldehyde group in the case of aldoses and ketone group in the case of ketosis, they react with the alcohol groups present in the neighboring carbons. That is, you can see hydroxyl groups are there. These are the alcohol groups, isn't it? So, the aldehyde group or the ketone group, they can react with the hydroxyl groups present on the neighboring carbons. Okay, and in such a way, they can form hemiacetals if they are aldehydes. If they are ketoses, they form hemiketals. Okay, this is what happens during cyclization. This is a reaction. Okay, you can see here the aldehyde, it reacts with alcohol. Okay, here it is given as separate molecules, but what happens when it is in the same molecule, the hydroxyl as well as the aldehydes, if it is in the same molecule, what happens, we will see in the next slide. Here you can see, okay, the aldehyde, it reacts with alcohol. What is the resultant product form? The carbonyl, the oxygen, it gets converted to hydroxyl group. Okay, and the H from here, it combines with oxygen forming OH, and the remaining OR, it binds with the carbon here. Okay, so this condition is known as the hemiacetal formation. Similarly, when it is ketone, okay, of a ketose, okay, if it is ketone, the same product of this form, except that instead of hydrogen here, it will have a R2. Okay. We can see in this case what happens. So this is the formation of the cyclization of glucose. Okay, so here what happens is the aldehyde group, it reacts with hydroxyl or the alcohol group on the 5th carbon. Okay, that is what happens. Okay, we can see that this particular chain, it bends over the aldehyde. Okay, that is how you have to visualize. Okay, so this particular chain, it will bend over the aldehyde, and you can see, so this chain has bent over the aldehyde, and aldehyde is over here. Okay, C2 carbon, you can see C2 carbon. So when it bends on this, when this chain, it bends this way. Okay, you can see. 1 minute. So what happens? The whole chain, it bends over the aldehyde. Okay, so what happens? The carbon here, it comes to this position, hydrogen into this. You can see hydrogen towards it. Okay, right? To the upper side of the plane. Okay, hydroxyl below the plane, right? Then this is the second carbon. Third carbon again. What happens? Hydroxyl is towards the upper side of the plane, while hydrogen below the plane. And fourth, it is just the opposite. And then finally, fifth carbon atom. Okay, what happens here? So when it reaches over here, fifth carbon atom, hydrogen, hydroxyl, CH2H. Hydroxyl is reacting with this one, isn't it? Sorry, you can see here. Okay. So this hydrogen is reacting with the aldehyde here. Okay. So what is remaining? Hydrogen is there, CH2H is there. So this extends like this, above and below the plane. Okay, what is the plane here actually? This carbon ring is the plane. Okay, and all the molecules which are directed upward, it is above the plane, and all those molecules below the chain, it is below the plane. Okay, I hope it is clear. Okay, so hydroxyl, that is alcohol group, reacts with the CHO. What is the net result? You can see this is how it forms. Okay, the hydrogen on the hydroxyl group, it breaks from here and it then combines with the oxygen. So it forms OH. Okay, so this becomes O, oxygen alone. Okay, so there forms a bond between oxygen and carbon. Okay, and as a result, what happens? Hydrogen and hydroxyl gets attached to carbon, the first carbon. Okay, clear? Now you can come back to the linear chain. This is the linear chain, or we call it as an open chain of D-glucose. Okay, now what happens is, in the open chain, we already mentioned that there are 1, 2, 3, 4. 4 asymmetric carbons are there. So out of the 6 carbon atoms, except the CHO and CH2OH, the rest 4 we have are asymmetric carbon. So in the open chain, there are only 4 asymmetric carbon. And depending upon the number of asymmetric carbon, we can have 2 raised to n or 2 raised to 4. In this case, 4 asymmetric carbon, so 2 raised to 4 stereoisomers, isn't it? 2 raised to 4, it becomes 16. 16 isomers can be possible with D-glucose when it is in the open chain. Clear? This is how the cyclization happens. How do the cyclization happens? Cyclization happens when the aldehyde group, it reacts with the hydroxyls on the neighboring carbon. Okay, on any of the neighboring carbon. Here what is happening? The aldehyde group, it is reacting with the hydroxyl on the 5th carbon. Okay, that is how the cyclization happens. Okay, during the cyclization, what happens to carbon 1? You can see what are the valencies, how the valencies are filled. In the first carbon, after cyclization, the valencies are filled, the first with oxygen, second with hydrogen, third with hydroxyl, fourth with CHOH. So all the 4 valencies are filled with 4 different groups. What has happened to the C1 carbon? C1 carbon also had become asymmetric. Okay, when the D-glucose linear chain, it gets cyclized, 1 more asymmetric carbon gets added up. Okay, and in this asymmetric carbon, or this whenever there is an asymmetric carbon, it will become optically active at that position, isn't it? So with this new asymmetric carbon, 2 isomers are possible. One where hydroxyl is extended downward the plane, and one in which the hydroxyl is extended above the plane. Okay, above the plane in the sense at the same position as that of the CH2OH. Okay, so when hydroxyl group is above the plane at the same level as that of CH2OH, we call this as beta form. Okay, so this is the beta form. And what is this then? This is the alpha form. So these 2 forms have arisen because of the cyclization of D-glucose. Okay, so due to the cyclization of D-glucose, two new isomers have arisen due to cyclization of D-glucose. Actually, one new what you call asymmetric carbon has arisen, and it will result in two isomeric forms. And these two isomeric forms, which have new ones formed, they are known as the anomers. Okay, so isomeric forms of monosaccharides that differ only in their configuration above the hemiacetal or hemiketal carbon. Okay, which is the hemiacetal carbon or hemiketal carbon? This is that one. This is also known as anomeric carbon because it is the anomers are because of the arrangement of molecules around this carbon, isn't it? So this is known as anomeric carbon. These are known as anomers or the anomeric isomers. Clear? So we have the anomerism or anomers. We call the isomers. We call it as an anomer. Okay, and that particular carbonyl carbon which is responsible for the formation of anomers, they are known as that. It is known as anomeric carbon. Okay. Now we can see. Okay, so that is about the anomerism. Now, when we during the cyclization process, what has happened? The glucose, a linear chain, has got converted into a six-membered ring, isn't it? 1, 2, 3, 4, 5, and 6. Okay, the sixth position is occupied by oxygen. So, but it forms a six-membered ring, right? Glucose, it forms a six-membered ring. Or in the case of ketone containing sugars, it would have been a five-membered ring. Okay, if it was a ketohexose, it would have formed a five-membered. That will be looking at. Okay, now because the five-membered structure, it resembles the organic molecule furan. The derivatives, they are known as furano. And since six-membered ring, it resembles the pyran structure, we call it as pyrano. Okay, so I hope you have studied furan and pyran in your chemistry classes, and there you can see this is six-membered ring with oxygen as one member in the chain. Okay, so this is actually a pyran structure, right? Pyran, typical pyran structure. You can see here. Yeah. Okay, so this is a pyran structure. Okay, and hence, since the linear chain, when it gets cyclized, in the case of glucose, it forms a pyran structure. It is otherwise known as pyranose. Okay, and so it is D-glucopyranose because the pyranose structure it has started with a D-glucose linear chain. So that you can see a D-glucose linear chain has resulted in the glucopyranose structures during cyclization process. So this is D-glucopyranose. Now, with respect to the C1 carbon, you can see hydroxyl group below the plane. This results in the formation of alpha D-glucopyranose. And when it is above the plane, just like this, it forms the beta D-glucopyranose. This is the six-membered pyranose structure which is formed from glucose. Glucose is a aldohexose. But what happens in the case of what you call fructose? Fructose, it is slightly different because it is a ketose. Okay, and